Hey guys, let's have a look at this question. You have a uniform conductor rod of length L and mass M. It's hinged about one of its ends and it's resting on a conducting support such that initially the rod is horizontal, right? A battery of EMF V is connected across the rod of negligible resistance as shown in the figure. A uniform magnetic field B is present perpendicular to the plane of the paper. Okay. The switch is closed at t is equal to 0 and the rod is just able to reach the vertical position. Then from this we need to answer what is the amount of charge which is flowing through the rod, the angular velocity of the rod at the moment of leaving the contact. When the rod makes an angle of 30 degrees to the horizontal by rotating upwards, the EMF induced across the ends of the rod is equal to this value. And just after leaving contact, what's the EMF induced across the ends of the rod, right? Okay, so this is your conducting rod which has a length L and mass M. This is hinged about one of its ends as shown over here. The rod is initially horizontal and then you have a battery connected to this rod. Then your switch is closed at t is equal to 0. We have a magnetic field in the inward direction, right? It's mentioned that the rod is just able to reach the vertical position. So we'll first make use of that idea. If this rod is just able to reach vertical position, so first of all we'll have to think about why this rod is able to reach the vertical position, or why is this rod even going to the vertical position. So after we close the switch, there will be a current flowing through this rod and the current flowing through this rod will be in this direction. You have a magnetic field acting in the inward direction here, right? So because of this, there will be a force acting on this rod, and the expression for the force acting on this rod is equal to IL bar plus B bar, right? L bar here is in I cap direction, B bar here is in minus K cap direction, so I cross minus K will be equal to J cap. So I'll have a magnetic force acting in this direction right now. So basically this magnetic force will lift the rod up. This magnetic force will lift the rod up. But the thing to notice over here is once this rod gets lifted from that position, there'll be no more current passing through it because the contact is being broken over here. There's no more contact. This rod is no longer in contact with your circuit. Your circuit will look like this right now. So that means there'll be no more current flowing through this right now. So this force will be acting for a short interval of time. This will be like an impulsive force over here. And because of this impulsive force, there'll be a torque acting on this hinge, which will give it an angular velocity. Right, so this angular velocity is being gained by the rod because of current passing through this rod for a very small instant. This is now acting like an impulsive force over here, and because of this angular velocity, it's able to reach the vertical position right now, right? So I think answering option B will be the easiest first, because now I can just write the angular velocity which this rod must have gained should be such that it should be able to reach the vertical position. So your rod should go from this position to this position. It's just able to reach the vertical position implies that its angular velocity at this position is equal to 0. So this is just a matter of using conservation of energy. I'll just say half I omega squared. Your initial kinetic energy should convert into potential energy. So that is equal to mg of L by 2. I value for a rod is ml squared by 3 in this case, into omega squared should be equal to mg L by 2. M and 2 gets cancelled. So one L also gets cancelled over here. So you'll get omega value to be equal to under root of 3g by L. Right, so your option B is correct. That's the angular velocity the rod requires to reach a vertical position right now. Right? Okay. And now why did this rod gain this angular velocity? The rod gained this angular velocity because there was a force acting on this. There's a magnetic force acting on this rod for a very small time instant. Right? And the magnetic force expression is ILB. We can't calculate I over here because we don't know any resistance and all. But now I know what angular velocity has gained right now, right? So we'll make use of the idea of impulse to solve this question. So your torque due to the magnetic force, we can assume that the entire magnetic force is acting at the midpoint because magnetic force is acting equally on all portions. So your torque due to your magnetic force then will become equal to F into L by 2. So your angular impulse due to magnetic force will then become equal to integral F into L by 2 into dt, and that should now be equal to I omega. That should now be equal to change in angular momentum right now. Right, what is this F equal to? This F will be equal to ILB. This F will now be equal to ILB and into L by 2 into dt, and that should now be equal to I omega. L doesn't vary with time, B doesn't vary with time. The only thing which can vary with time over here is probably I itself. So we'll now write this as L squared d by 2 integral I dt is equal to capital I omega, and this integral I dt is your charge flow. So your charge flow over here will be equal to 2I omega by BL squared. It will be equal to I omega by BL squared. So substituting these values over here, this will become equal to 2 into ml squared by 3 into omega divided by dl squared. L squared gets cancelled. So your charge flow then is equal to 2m omega by 3b. And we have already found out the value of omega. Your value of omega was equal to nothing but under root of 3g by L. So your value of charge flow will be equal to 2m by 3b. 2m by 3b of under root of 3g by L. If I take this 3 inside, this will become equal to 2m by b under root of g by 3L, right? So option A is also correct. Option A is also correct over here, right? Option C and D are based on motional EMF. So you can try this out, but I would read this for now because we haven't, at least we are not going to be discussing motional EMF right now. But it's all option C and D. You will just have to make use of the formula since you already discussed motional EMF a bit. You'll have to make use of the formula B omega L squared by 2, right? But for moving charge and magnetism, these two options are what we need to be discussing. And this will be your answer for these two options, right? Hopefully this question made sense. See you guys in the next question.